I think it kind of just goes to show that a PhD is so much more about enthusiasm and sort of dedication than it is about having that expertise already.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. This week your hosts are John Perney-Fisher.
Hello.
Ricky Bahir.
Hello.
Tom Harvey.
Hello.
And our special guest this week is Áine O'Brien.
Oh.
How are you doing, Áine?
Yeah, not bad. Loving life in isolation.
And from outer space, I see, wherever you are there. So you're a PhD student at the University of Glasgow. Would you mind telling us what your project is about?
Yeah, sure thing. So my PhD is focusing on Martian habitability and astrobiology. I'm all about trying to understand if Mars ever had the right ingredients for life to form in terms of the building blocks of life. So life as we know it is kind of based on carbon. Every life form terrestrially is based around carbon molecules. So it stands to reason that if we're going to find life on Mars, it's probably quite likely to be a carbon-based molecule. So I'm searching for carbon and its various molecules it can form in rocks from Mars that come in the form of Martian meteorites.
Amazing. So what Martian meteorites do you look at?
So I look at a sort of a mix, really. For the most part, I get little cast-offs from other people in my department, little chips. I'm talking less than a gram here of sample that was left over from another experiment or bought by another project, just simply because I don't have a lot of cash to throw around, and some of them are $6,000 a gram, so I don't really have that money hanging on the back of my sofa. So
you just wait until you're a postdoc. That'll all come out, don't worry.
Yeah. So there's sort of around about half a dozen samples that I look at. Mixture of some meteorites were seen to fall. So there was one meteorite that fell in 2011. It's called Tissant, and this is a piece from Mars, and I'm lucky enough to get a bit of that. And that's really useful because we know that it wasn't hanging around in the desert where it fell for too long before someone picked it up, because they literally saw it fall from the sky. And that's useful for me because I'm looking for organic molecules in these meteorites, and if they've been sat on Earth for 30,000 years, how can I prove that these bits of carbon are Martian and not from Earth? Well, that's a problem. So it's a contamination issue. So I try as much as I can to get fresher meteorites samples, just for the sake of, it's easier to say that, well, that stuff is probably not from Earth.
Are they quite easy analyses to do then? Are they quite high abundance, some of these organic molecules?
Yeah, that's a good question. So the stuff I'm looking at predominantly is basically kind of like a tar, a really sort of small blob of tarry substance that you find hosted in igneous minerals that are in these Martian meteorites. And they're kind of like 50 microns across, so we're talking really small little black blobs that sort of just look like blobs of tar. And they are pretty prolific. I'm not the only person who's studying these things, and the people who are have found them in all the different there are lots of different categories of Martian meteorites, 3 or 4 different main categories, and people have found them in most of those samples. And yeah, so they're pretty prolific, despite the fact that I've only got these tiny pieces and I managed to find them in there. Shows that it sort of stands to reason that there's quite a lot of it around.
That's crazy.
But they're just very small.
Because I guess you don't normally associate sort of igneous rocks with organic compounds generally.
Right, yeah, exactly. In fact, and that's one of the things I'm trying to figure out studying is, well, how on earth does this stuff form? Because we don't really see this in Earth rocks. Well, we do in one place on Earth, and that's on Svalbard, which is an island kind of halfway between the top of Norway mainland and the North Pole. So it's this frozen land, Arctic tundra, near the North Pole. And on Svalbard, they've got these volcanic complexes where the magma is kind of solidified below the surface in what we call it's this thing called a xenolith. But basically, there's a volcanic complex on Svalbard where they see the same formations in the igneous rock. You see these same very similar blobs of tarry stuff forming that match quite well with what's been found in the Martian meteorites, which is pretty cool because it means that it's a really cold place and Mars is really cold, and there's similar rocks there. So NASA actually spent, I think, 10 years every summer as you can get in the Arctic, testing out a lot of their rovers there, because they knew there were similar rocks to Martian material, and obviously with it being cold, it's a pretty good place to test out rover stuff too.
Yeah, and I suppose it makes sense if we're looking for analog environments. You're going to be looking in the more extreme places on Earth rather than places where we live and can survive happily.
Yeah, exactly.
So you said you're working with very, very small samples for this. What sort of instruments do you use to analyse them?
So I use a lot of, sadly, very expensive, high-powered instruments that I don't often have a lot of time access to. The main way to identify this stuff is with a special kind of what we call Raman spectroscopy. It's basically you fire a laser at a thing and the laser bounces off, and the amount the light changes by when it bounces off tells you what the stuff is made of. And this kind of carbon has like a really distinct signature when you do that. But because my samples, or this tarry stuff in my samples is so small, I can't use just any old laser just firing at a rock. I have to use a special kind of setup where they've basically taught's the wrong word. I have to use a setup where they use a load of different lenses to kind of focus the laser inside my sample within a 300 nanometer focal range, so super focused.
Nanometer, wow, yeah.
Yeah. So if you think light is 650 nanometers thereabouts, this is a focal range smaller than the wavelength of light itself. Mad. Optics people are so smart. Anyway, so luckily someone figured out how to build that. And I go over to Washington, DC and play with the machine where they do that. So I look for these areas in an optical microscope, basically just looking for blobby tar-like things. And then I put them in this laser, and if the right signature comes out of the computer at the other end, then I say, great, there's stuff there. But that just tells me there is organics there, that it's some kind of tarry stuff, but it doesn't tell me much more than that. So I then go one step further and I say to the fancy electron microscope people in the physics department here to take a chunk of my meteorite out, and by a chunk I'm talking 100 nanometers thick and maybe 20-30 microns wide chunk out, and then I take that to a giant metal donut in the Oxfordshire countryside, otherwise known as the Diamond Light Source. So this synchrotron basically has a wonderful byproduct of firing subatomic particles round in a circle. That great big range of X-rays come out of it, and I can harness those X-rays. I fire them at my 100 nanometer thick piece of Mars, and that X-ray interacts with the sample on a kind of atomic level, basically. So I can detect particular bonding groups. So I can say, oh look, there's a carbon double bonded to an oxygen there, or oh look, there's an alcohol group or a graphite group. So that stage I can then really say, oh look, there's what's happening in a kind of atomic arrangement level here. So they're the kind of two main techniques I used, and they're ones that are kind of used as quite a standard in this kind of area. But more recently, I've been trying to develop other techniques that tell me even further what's going on a less small scale, in terms of it's not just I don't know exactly where it's come from, but I can find all the molecules in a sample rather than having to really zoom in. Because you imagine it's quite time consuming to think, okay, I'm going to look at that blob and then I'm going to fire a laser at it, and then I'm going to take a chunk out and then put it in the X-ray thing. I've also been working on techniques to say that if I give you a whole crushed bit of Mars, how can I take all the organic matter out of there and just basically be told, here's all the stuff that's in there. And that's what I'm working on at the moment with basically mass spectrometry techniques to do that.
That's cool that you can measure such small things, though. So
Mm.
have you been able to measure quite a diverse range of different compounds? Has it been quite surprising at the sort of range of material that are there?
I would say nothing has been super surprising yet, but maybe it's just because I don't understand it well enough. I don't know. It's what we call macromolecular, so it's quite just basically means really big, lots of like we'll call it aromatic, like basically rings of carbon, and then you find a few other little bits on the side, like bits on the edge of it, so alcohol groups, that kind of thing, but nothing too exciting at this point. It's very much just kind of your run-of-the-mill, quite big tarry substance. The best similar thing on it that might be familiar is like a kerogen is the sort of thing we have on Earth that's like that.
Yeah. So where are these things coming from? Are they coming from the crust, and then the volcanoes are dragging this stuff up from somewhere deep in mid to low crust levels, or?
Great question, and that's one of the things I'm trying to figure out is where this stuff has come from. So there's two main ideas in the community, and like everything in planetary science, don't we love to argue about where things come from? So the two main hypotheses of where this stuff comes from is one, that it is indigenous to Mars, so it's native, and comes from inside the planet. We think, that side of the story thinks that this stuff comes from inside the mantle of Mars. Now, it's interesting in terms of chemically what must have been going on for that to happen. Anyone familiar with kind of redox reactions, in order for this stuff to form, it's got to be quite a reducing conditions, we call it. So if this hypothesis turns out to be true, that it is Martian mantle derived, then there must be quite reducing conditions going on in the Martian mantle at the time where this stuff kind of crystallizes. Conversely, the other main hypothesis is that this stuff is deposited on Mars by other meteorites. So we know that Mars has been bombarded by other space stuff. You see it's covered in craters. And we know that lots of meteorites that aren't Martian are full of carbon.
Yes.
Carbonaceous chondrites, right? So some people are trying to say, well, is Mars born carbonaceous, or was carbonaceousness thrust upon it? That's the sort of thing I'm trying to answer. Or indeed, what's probably likely is it's probably a mix of both, because it is going to get hit by meteorites, and this stuff is inside the igneous minerals, so it's probably likely it is Martian mantle derived. But that's one answer I'm trying to find, or at least contribute to our gradual arguing one way or the other as a community. And in fact, one of the a sort of side project, I guess, or I don't know what the right word is, but a guy I'm collaborating with, Dr. Alistair Tate, he's taken a CM2 chondrites. This is a carbonaceous chondrite called Giblet Winselwan, which is just a great name.
Yes.
And he's working on this idea that Mars must have Martian meteorites on it. He's doing experiments to simulate Martian conditions in the soil and see what that does to the organic matter in Giblet Winselwan, to see how it compares to my data, to see is it similar. If we provide a Martian soil-like conditions to a non-Martian meteorite, what does the organic matter look like compared to when you see the actual organic matter in the Martian meteorite? So we're sort of working together on that.
So just when you're talking about soil conditions on Mars, I guess people might not know, how do you actually know what soil conditions on Mars are like?
Great question. And in the context of this, we're just really lucky because of the rovers that we've had there since the Viking landers back in 70s. Yeah, back in the 70s when the Viking landers first landed. They found evidence for basically, we call it strongly oxidizing conditions in the Martian soil. They call it perchlorates, particularly. It's basically a chemical that causes basically stuff to burn. And we think it's really prevalent within the Martian soil. So that's what we've been treating our non-Martian samples with, because we see with the experiments on the rovers that we basically think that most of the organic matter that's been found or would have been found is kind of burning up in the laboratories on Curiosity, etc. So it's sort of why there's actually been very little organic matter found by, for example, Curiosity, etc. It's because we think it's because there's this stuff in the soil that as soon as you put it in these onboard experiments, if you like, it just causes it to burn up before it's detected. And you can't put a synchrotron on Mars yet, so we can't do the same things that I've been doing.
Are there any samples that you haven't been able to analyze that you really would like to, that might help us try and address some of these questions?
Oh, always more, I think, is the main answer. As fresh as possible was always good.
How difficult is it to worry about terrestrial contamination?
Well, how much do you want to get published, John? And who is reviewing you? Ain't that the thing? No, in all seriousness, it is the main, unless you have, for example, really clear isotopic data. Mars has got quite different isotope ratios to Earth in terms of deuterium and hydrogen. And if you aren't able to do that, which is really hard to do with tiny, tiny samples of carbon, unless you have isotope data, it's very difficult to prove to people who don't know the systems really well that this stuff is Martian, especially until Curiosity found, we call them thiophines. That is a paper by Eigenbroder et al. Who came out in 2018. You should have seen me that day. Oh my gosh, because it changed my PhD completely. Because it was like, finally people believe that you find this stuff on Mars, right? Until then, it was real battle to convince people that actually this stuff is Martian. But the fresher your meteorites are, that it's harder to say, look, this stuff has come from Earth, when if it's literally just come out of the sky.
Well, also the fact, as you say, if they're within mineral grains, that's going to be hard to get in there. If they were all in grain boundaries, then that would be a bit more difficult to argue for, I suppose.
Yeah, exactly. And that's what we do. We look for them hosted in the mineral, far away from cracks. I look at thin sections, so these are bits of rock on glass sides, and I find these blobs that are below the surface, so there's none of it exposed, that kind of thing. And yet still people I've been collaborating with have been having issues from time to time with reviewers saying, no, it's just terrestrial. But as I say, it was a big turning point, the Jen Eigenbroder paper of 2018, where they finally matched up the stuff with the meteorites. It was a good day.
What drove you to pursue this project in particular?
Well, that's a good question. So I'm quite lucky in that my PhD funding comes from I say lucky, I don't know if that's the right word, but I'm funded by a bequest to the university. So thanks to someone who died a few years ago, they basically fund a PhD every few years out of the investment of the bequest. And it means that it's not tied to any particular outputs, tied to anything, and it's just awarded to a student, which meant I had a open book, free reign to do what I wanted. And originally I was going to be doing some alteration based stuff, so looking for kind of evidence of weathering on Mars. But just before I started, my supervisor had applied for funding to do this for another project, and she didn't get it. And she was like, I've got this other thing that I wanted to do, but she couldn't because she didn't get funded. She was like, would you like to do it instead? And I was like, yeah, that's way more interesting. Martian alteration is cool, but this is super timely. There's lots of missions coming up that are focusing on this stuff, so it's really cool.
Yeah, so I guess that leads nicely into what I was going to ask next. It'd be great to hear how you've been involved with ExoMars and the Rosalind Franklin rover.
Yeah, for sure. So ExoMars is a two-part mission. One part, the Trace Gas Orbiter, which is happily whizzing around Mars, and the second part is the Rosalind Franklin rover, which will now be launched in another 2 years' time, sadly, as of a few weeks ago. And the rover its main kind of aim is to look for signs of present or past life on Mars, and nicely named after Rosalind Franklin, as she was instrumental in the discovery of the structure of DNA. So my PhD is really well timed to complement the data set of the Rosalind Franklin rover. It's going to be having a Raman spectrometer. So this is that laser thing I was talking about on board. We've never had one of those on Mars before. There's also one coming up with the NASA 2020 Perseverance rover as well. Just a different wavelength of light there. So big point is when we send our rover to Mars send Rosalind over there to fire her lasers. If it matches up with the data I'm getting, we know that the sort of systems are working right. Beyond that, it's got a fun little drawer called MoMA, which I think is a really cute name, and that's the Mars Organic Molecule Analyzer. Yeah, Mars Organic Molecule Analyzer, MoMA. And this is basically a drawer full of different experimental suites that are designed for looking for organics, because as I said, life as we know it is based on organic matter. And most of these, this instrument suite has a lot in common, and in fact is the same techniques I've been using here on Earth with my Martian samples. So what it means is I can get data of what if we put a Martian sample into this machine and we know it's got organics in it because I validated that with my earlier work with the Raman. I can then say this is what you'd expect to see, and I can indeed also compare it to known materials. So if I know what an organic material looks like, I can put it in that machine, we know what the spectrum is, and then we can compare it with what Rosalind Franklin sends back to say, look, okay, we know that, I don't know, there's a kerogen there or alcohol or something like that.
That's going to be a real game changer then, really, I suppose.
Yeah, it's good. It's going to be good, especially the Raman, because there's no worries there with the perchlorates that I was talking about. So there's not an impact from the fact that the soil's got this oxidizing stuff in there. And indeed the same for the Mars 2020 Perseverance rover. And what's really exciting about that one is that the 2020 rover is going to be caching samples. So that means basically storing them ready for, in a few years time, hopefully, touch wood, you can't see, but I'm touching my desk here. At some point in the future, we're going to bring samples back from Mars. So they're not going to be meteorites. We're going to have what we call Mars sample return. And that's when my project really kicks in, because we are going to need to know exactly what the best way is to analyze for organic matter in the most efficient way. We're not going to have very much that's going to come back. It's really, really hard to get to Mars, and it's even really, really, really hard to get back. So hard we still haven't worked it out yet. So once we do that, there's going to need to be a pipeline saying that, okay, this is what you should do first, here's what you should do next, in terms of pulling out as much information you can from these tiny samples. And that's very much a question I'm trying to answer, is what's the most useful tool for looking at organic matter, both in person. So obviously, like I said, no synchrotron on Mars, but when we have Mars sample return, someone's probably going to want to put that in a synchrotron. So again, it's a case of evaluating which synchrotron techniques are best, that kind of thing.
And do these techniques break down the organic matter, or is it preserved?
Yeah, very good question. It depends on the technique. So that's one of the good things about, one of the interesting things about Raman is for the really big ringed kind of sludgy stuff, nothing really happens. The light just bounces off and it stays as is. One thing I have found in my PhD is that there's been sort of bubbles of what we call more labile. It basically means more reactive, kind of simpler organic matter in there that has changed and become heated by the laser and turned into that more sludgy kerogen stuff.
Oh, right, okay.
Just under the laser heating, and the laser's only something like 50 degrees. Obviously it's very focused energy, but it's not that hot. So that's another part of it, is one of the techniques we use to look at it changes it. So when the Rosalind Franklin rover's wheeling around in a few years time, when she fires her Raman laser at something, she might actually change it while she's looking at it. So that's another thing I'm trying to investigate, is how can you pull out from the initial data and the end data how much it's changed by.
Do you think any of these compounds then that you're analysing, or that the Rosalind Franklin might be analysing, will be real? Is there any one particular molecule that you could look at to say this is definitive sort of evidence of life or proto-life?
Not as far as I know in terms of definitive, especially because we don't know what Martian life would be like. My instinct would be if we could investigate chirality. So life as we know it, the molecules in us are all kind of either what we call right-handed or left-handed. It's basically that you can't put your left hand on top of your right hand and it be the same in any way. Like if I do that, I've got them facing different ways, right? Molecules are the same, and it turns out life kind of favors one to the other, whereas natural organic matter doesn't. as in just like non-life based. So if there was some way of investigating that, maybe. That's not particularly my area. I guess I'd say I'm more like the really fundamental with the ingredients there. And then someone much cleverer than me can then figure out how that would then become the next step to life. And I think that's a big question in astrobiology, is how did that happen with us on Earth, right? We don't know what the big step was from primordial oozy sludge to cells and stuff. Yeah,
but that's really exciting though, the fact that we're building a picture though that some of this primordial sludge was potentially there.
Yeah, exactly. And what's even more interesting is that until recently, we thought that the radiation environment at the surface of Mars was going to be too strong for this stuff to survive. Effectively, you're giving organic matter like extreme sunburn by putting it on the surface of Mars. But then that paper that came out, Eigenbroder et al. 2018, sorry I keep talking about it, this is great, showed that actually this stuff can survive. What was interesting about it was an organic molecule, carbon, hydrogen, that kind of thing, but it had a sulfur atom in the ring, replaced by one of the carbon atoms was replaced by a sulfur atom, and there's an idea that maybe the sulfur was kind of keeping it together, holding it all together and resisting that radiation more. That's one of the theories anyway. So we'll see.
That's really cool.
So I believe that you actually came to planetary science more from a physics background and also more from a teaching background as well. So how has it been moving into the world of planetary science from that?
So my undergraduate degree was in physics and astrophysics. I graduated in 2014 with a bachelor's degree. And it was interesting because when I was really young, when I was a teenager, I loved space, but I really thought black holes and cosmology and galaxies were going to be my thing. And then I got to university and the maths got really, really hard. And I also learned I can't really think like computers. A lot of physics degrees are really based on programming and coding, and I cried about Python and C more than anything else in my degree. So I sort of realized that because most astronomers are very programming, data science based, or just any kind of coding really, that wasn't for me. So that was my sort of early discovery, if you like, during my degree. I did a lot of outreach in science communication from the beginning as well. It was just great fun going into schools, talking about space. Used to help run a summer school called Space School UK, which is a summer camp for teenagers interested in space. And kind of through all these activities, I realized I really loved educating people about science. So I went straight from my undergraduate degree to teaching high school physics and astronomy for 3 years in the southeast in Suffolk. And I had a great time. I really loved it. But over time, I started to sort of get jealous of my own students because they were learning new science and I wasn't. And then at the same time, I think it was after my second year of teaching, I went on it was kind of a symposium, I guess, run by the European Space Agency for teachers across Europe to kind of come together and learn about what ESA does and kind of put things into the classroom. So they were giving us hands-on ideas for teaching and we were kind of feeding back to them on how that would work. And during that week, there was a talk actually by one of your previous guests, Elliot Carter.
Yes.
Yeah, what a guy. He gave a talk, I think it was like nearly 2 hours long, about the landing site, in fact, choice for ExoMars. And I just sat there the whole time like, like, you know, the emoji of the heart eyes, that was me learning about this stuff, right? And I came away from that week thinking, oh gosh, I do really miss this. And so I started thinking about my options, like, do I go do a master's? Because all I had was a bachelor's and my teaching certificate as well. And it was really nice. I went back and spoke to a few of my old lecturers from my undergraduate degree at Leicester. And I said to them, like, hey, I kind of want to get back into this. And one of them said to me, look, you've got a good first class degree. You've got a postgrad. Okay, it's in teaching, but like, it's fine. You could just apply straight for a PhD. And that had just never even occurred to me. Like, no one I knew did PhDs without a master's in astrophysics. Like, it just wasn't a thing. So yeah, then I was like, oh, okay, well, I'll look at that then. And I really wanted to move to Scotland. I wasn't the biggest fan of living in East Anglia. It's very flat, and I like mountains a lot. So Scotland seemed like the natural place for that. And yeah, so that's where I am. It was quite a shift, especially when I first started, to learning just like loads of geology words that your average first year would know, and I didn't. But one really good thing was that they, from the beginning, because of my teaching experience, they put me to teach first year tutorials in the department. So I would get told the science that I needed to know, and then I'd obviously, having had the experience of teaching, I'd find that side of it a bit more easy. So I found it really helpful doing loads of teaching in the department, learning the fundamental stuff to teach it, and then it's kind of informed myself. I think I'm plagued by mega imposter syndrome, that my PhD involves very little physics other than like understanding how the lasers work. But I think it kind of just goes to show that a PhD is so much more about enthusiasm and sort of dedication and just that desire to learn and sort of deep dive into stuff than it is about having that expertise already. But that is something I took. I mean, I'm 2.5 years, 3 years in now, and I'm only just now kind of accepting that I am allowed to be here, I guess. You think, oh, I don't know it, someone else must, but actually no one really does, because you are at the forefront of figuring science out, right? So
yeah, especially with planetary science, you can't do just BSc planetary science. It's only when you get to master's or PhD level that you can start to actually learn more about it. So yeah. We do know more than we think, everyone.
Yeah. And I think when I first started, I thought I'd be really unusual being a physicist in a geology department. But actually, as I've gone to conferences, particularly in planetary science, particularly in our field, there are quite a lot of us who switch one way or the other.
Yeah.
And yeah, I mean, a lot of what I do is organic chemistry, and, I've just learned it now, and that's fine,
You're still getting the opportunity to do lots of outreach stuff, because you're in charge of the it's called Roving with Rosalind, right?
Yeah, exactly. So a friend of mine, Sarah Matagian, she's a PhD student at the Natural History Museum. So she and I run a outreach project, as you say, called Roving with Rosalind. Basically, about a year ago, Sarah was telling me how she had this idea of how she could bring or like downscale what the rover will be doing into the classroom. So give students in schools the eyes of Rosalind, effectively. So she had this kind of idea of a couple of activities that she developed within her own just sort of small scale outreach stuff that I just thought, wow, that would be great. I can just see immediately how that would fit into the classroom. So we got given about £20,000 funding from the UK Space Agency to develop and build kits to go into schools where they can effectively do their own little ExoMars mission. So it's from the very beginning stages of a mission. They can do things like design their rovers in terms of the decisions that get made by systems engineers. So how many wheels would you like? That's the thing that systems engineers going with their Mars rovers have to decide. So we get them to think about that. Then we've got these little Lego they're called, programmable rovers, where they can build out of Lego their own little rover, and then they can actually program it to explore. So they have to design a route on a giant kind of lino fabric printout map of the landing site. They have to design a route to explore Mars and then program their little rover to do it. And then as they get to certain sites, they're then given different scientific activities to do that are accessible versions of effectively what the ExoMars rover will be doing. And it goes back to what we were saying, space is accessible to everyone. Everyone has imposter syndrome and thinks, oh, I'm not clever enough to do that. But if you show a child that actually they can do the sort of thing that a rover does, and a space science data person looking at Mars mission data is looking at, like, that just kind of takes away that barrier of them thinking it's not for them. And for me, that's something I'm really passionate about, is that the space sector has a duty, I think, to sort of diversify we're going to expand so much. The UK Space Agency want the sector to be worth, I think, 30 billion by 2030. We do not have the workforce for that at the moment. I think we have to double in size. And if we aren't actually harnessing the power of all the different groups of society from a grassroots level, we're not going to be able to achieve that. And a lot of studies have shown that a lot of young people who feel the biggest sort of barrier from science or STEM, if you like, a lot of the people who feel that it's because they've had less exposure to STEM in their lives. So part of the aims of this project is that it's a kit that can be sent to schools in far-flung places in the UK where, you know, they may not have had the chance to visit a science museum because, I don't know, they live in John O'Groats, right? So we're kind of trying to address that aim of, okay, let's engage with audiences who've really not had that exposure and show them that it is a doable thing. You don't have to be some kind of Einstein or like some kind of Sheldon from Big Bang Theory to work in space, because it's not about that. It's about enthusiasm and hard work. So,
have you got a sense of how successful it's been at different schools?
Well, the annoying thing is we just finished making the kits, and I mean
no.
And then the shutdown happened. So right now, we have all this stuff. We finally finished creating, ordering all this stuff. And now we just have to sit and wait, which is a real shame, because the plan had been to start testing out this coming term after Easter.
Okay.
So we have to sit and wait now, which is such a shame, because I just want to get kids playing with it. But
well, have you got a website?
So we, at this point, we have an email address, which is, I think is, hang on 2 seconds.
Or we can put
it's rovingwithRosalind@gmail.com, and we are basically, there'll be a section on the spacecareers.uk website dedicated to this. That's just being finished up at the moment. There's going to be like a little BuzzFeed style Mars quiz. But at the moment, that's all we have. Just everything's all kind of in a state of flux with.
Cool. Well, we'll try and put some of that information in the episode description.
Sounds good.
Wonderful. Well, shall we ask our final question?
Yes.
Yeah. Okay. A surprise final question that we ask all of our guests is, if you could be doing something completely different, and fair enough if you're just like, no, I already do the coolest thing, I'm not going to answer this question. But if you could be doing something else, either in academia or outside of it, what would you want to do?
Oh, that's a great question. If I could be doing something else. It would be hard for me to say I would do anything outside of space. But if I was to leave the space sector, what would I do? In this isolation period, I have gotten really into baking. So to be honest, opening some kind of bread shop seems pretty appealing right now.
You've managed to find some flour.
Yes. So it turns out people in Glasgow aren't the hipsters quite that a lot of the rest of the world seems to be. Either that, or they just know there's so many, they really stocked up, because we've got plenty of bread flour. So me and my other half have been making 2 loaves of bread every week.
Really good.
It's been pretty great. No sourdough starter though, because I kill plants. I don't trust myself to keep a sourdough starter alive.
Well, that's a good answer. I mean, certainly our local high streets could do with a better bakery. So. Well, thank you, Áine, very much. That was a fantastic discussion. For all you listeners out there, if you want some more Earth and planetary science content, you can check us out on all the social media. We're at Earth Solar System everywhere, from Facebook to Instagram and everywhere else. Links will be in the episode description. And if you've got any questions or anything like that, or any feedback, do tweet at us at Earth Solar System. Thank you very much, and we'll see you all next time. Goodbye.
Thank you. Bye-bye.
Bye.